When they spontaneously transform, they can stimulate the transformation of other excited states around them. So you get something sort of like a chain reaction. So I can produce a very large burst of photons that are precisely defined as the frequency because they're all products of this transition, and are also precisely defined as the phase. And as a consequence, I can get a well-collimated beam. Well, now what we do to really make this happen is, of course, we have the exciting radiation coming in. But you then you confine the radiation inside the laser with mirrors. You reflect it back and forth. By reflecting this radiation back and forth, you're really pumping up the stimulated emission. Now you can decide when this is going to come out by using some sort of gating mechanism which suddenly releases this well-collimated beam, or producing a continuous stream, as in this example which is ceasing to work, by having a half-silver mirror at one side, so that you have emission bouncing back and forth in the laser, and a little bit of it is constantly coming out. And that's the way a laser works. Light emission from a laser. It's a way to get a beautifully collimated beam, which I can use as a pointer when it works. It's a way to get very focused energy, because the intensity of the beam remains in a well-collimated beam, so I can use it to transmit energy from here to over there. And there are applications of that sort. I can also use it as a very, very nice way to transmit information, because since I have a beam, it is well-defined in frequency and well-defined in phase. Anything that I do to that beam will be carried as information in a very clean way. If I just try to take a light, let's say, and modulate it to send a signal, I can of course do that. But the signal is contaminated by the interference of the various components of the light. With a laser, since everything is well-collimated, since frequency is well-defined and phase is well-defined, any minor modification I put into that laser beam will be carried with a laser beam and can be read at the other end. So almost all transmission of information these days is by lasers. Well, there's one more sophistication in the laser that I should talk about. The original lasers, the ruby lasers, were three-level lasers. That's what I showed you before. You have an excitation from ground state to an excited state. You then get relaxation to this state, that forbidden state, let me call it, because the transition is forbidden. You then excite the forbidden, and the transition goes back to the ground state. One problem with that is that if you happen to have white light floating around, if there is some stuff floating around that has that frequency, then I can get some problems. I'm stimulating emission with things that are out of phase I don't want to stimulate emission with. I can lose some efficiency because I'm forcing this transition or exciting this state when I don't want to. So there are some problems with this ruby laser. The first lasers were lasers of this sort. They work pretty well, but they could be improved. And the principal improvement, neodymium YAG and others, is the four-level laser. In this case, we choose a phosphor which has one additional property. When, same thing, we excite the phosphor to its excited level, it transitions to a forbidden level. But now we let that forbidden level be such that when it transforms back to the ground state, the state that it goes to is not the original ground state, but some other. And in that way, we can isolate the laser event from the transition. This transition is a problem over here in the three-level laser because every atom, every ion that's in there that's unexcited has this ground state. And therefore, any radiation that happens to have that frequency is in danger of falsely stimulating my radiation. Over here, the only atoms that have this state are the atoms that just underwent a transition, and they will quickly relax here. So there's almost no wasted efficiency in this four-level laser, and that's the kind of thing that we use now. Of course, now they also use things like free electron lasers and so on, which operate on somewhat different principles, but since they don't really use lasing materials, I don't need to talk about those. This is a very common laser that's out there. And if I knew what they were using in these laser guns, believe me, I would tell you, but I don't know, except that they solve some problems we weren't able to solve. Semiconductor lasers, here, basically, you just use a semiconductor transition. Here, you pretty much have the same thing. In this case, you use a semiconductor which has kind of the same properties. You will have a three-step semiconductor, something like this, which allows you to pump electrons into this central well, if you want, here. But they are trapped in that position. They're being swept forward under this potential, negative terminal here, positive terminal here. But there is a much higher band gap on the right-hand side. So the electrons that are swept into this well at the lower electron energies can't get over into this region, at least not at a very significant rate. As a consequence, we can pump a very high density of carriers into this region, such that we significantly exceed the normal recombination rate. We have too many carriers to recombine easily with these holes. And then we use exciting radiation to stimulate recombinations in this region. This is a kinetic event. What you're trying to do is pump electrons and holes into this well so quickly that they don't have, it takes time for an electron and a hole to recombine by natural processes. So if we pump them in at a high enough rate, we can dramatically exceed the recombination time and let these things just accumulate. So we have a very high population of electrons and holes sitting in this region. Then we can stimulate emission, speed up this recombination process by stimulating emission, by putting in a light of precisely the frequency for this recombination, and in that way we get a semiconductor laser. And it's the semiconductor lasers that are used, gosh, all over the place in communications and so on. Mainly gallium arsenide, because gallium arsenide has such a beautiful direct transition that it produces a very well-collimated beam. It's called a heterojunction laser. By doping the gallium arsenide, we control these, the band gap in these three regions and create the structure that I showed you here. Okay, that's what I need to say about optical properties. The next thing we want to talk about in the electromagnetic properties of materials are magnetic materials. Magnetic materials are also very important. Of all the kinds of magnetism that you would study in physics, there's really only one kind of magnetism that leads to important engineering applications, and that's ferromagnetism. So I want to get to that as soon as possible. But in passing, we have to talk about the other kinds of magnetism too. Sources of magnetism, unpaired electrons. If we have an unpaired electron, the electron has a spin, and the electron has a magnetic moment called a Bohr magneton. It's associated with that particular electron. So if we have a situation in materials in which we have unpaired electron spins, those unpaired electron spins will give rise to a magnetic moment, a magnetic field, and we can use that for engineering purposes. The most important kinds of magnets are those that have unpaired electrons in the inner core of the atom itself. This is what gives rise to ferromagnetism. The ferromagnetic materials are materials that have partially filled d orbitals, the transition metals, or partially filled f orbitals, the rare earths. And those are the ones that can have significant magnetic moments. I say can have because only a few of them do. We'll talk about that in just a minute. So let me first of all just talk about there's a second kind of magnetism which comes from the electron orbit, secondary magnetism. It's in the notes. I'm not going to talk about it here. The type of magnetism, there are really three kinds really. The first kind of magnetism is present in every material, and that's what we call diamagnetism. That's because the electron orbit is changed in a magnetic field in a way that opposes the magnetic field. Diamagnetism is weak magnetism in almost all cases. The only example in engineering where diamagnetism becomes important is in superconductors. So we'll put that off until we talk about superconductors. I'll just tell you what it is. The materials that have permanent magnetic moments at high temperature, these magnetic moments are disordered, and that gives rise to what we call paramagnetism. The individual atoms have magnetic moments, but the magnetic moments are disordered, so there's no net magnetic moment in the material. At low temperature, these magnetic moments can order, and they can order in one of two ways. They can order anti-parallel, in which adjacent magnetic moments point in opposite directions, in which case they cancel each other out. That's what's called antiferromagnetism. They can also order so that they are parallel, and this is what's called ferromagnetism. Ferromagnetism, parallel ordering, is much less common than antiferromagnetism and is the source of most good magnetic materials. There is a third kind called a ferrimagnet. I'll tell you about this in a moment. So let's talk about sources of magnetic fields. There are really three that you can be familiar with. If you just make a current loop, send a current going around the loop, you will create a magnetic field, which has a magnetic moment that's the current multiplied by the area, and it's in the direction of the normal to the current loop. To create more powerful magnetic fields, we usually use solenoids. And even the world's biggest magnets are solenoid-based, such as the things that people are trying to use for fusion energy now. They're coils, solenoid-based. If you have a whole bunch of turns, and a current is running through those turns, there will be a magnetic moment, magnetic flux, with a vector right down the bore of them, with a magnetic flux right down the core of that solenoid. And the magnetic field H is the number of turns, the current, the direction is the normal to the current loop. The third source of magnetic fields is a spinning electron. If I have a spinning electron, then the inherent magnetic field of the spinning electron is the Bohr magneton, MB. And here you just see an example of such a thing. Basic relations for the magnetic field. We talk about the magnetic field H and the magnetic flux B. The magnetic flux is mu 0 H, where mu 0 is the magnetic permittivity of free space. The mu is the permittivity is greater than or equal to 0. The reason that we treat both the magnetic flux and the magnetic field, well, there are many reasons, but the primary reason has to do with the boundary conditions on the magnetic field that lets us establish how the magnetic field changes as we go from one material to another. If we look at, suppose we have a material that has a spontaneous magnetism M. There's a spontaneous field set up in the material, for example, by ferromagnetism. The boundary conditions on that magnetic field in a field that is placed on the material are quite different depending on whether the direction of the external field is normal to the material of interest or tangential to it. The magnetic field is continuous across the tangential boundary. The magnetic flux is continuous across the normal boundary, just from the laws of magnetism. So if we have a field that is magnetized, and we put a magnetic field on it perpendicular, the magnetic field inside the material is reduced, such that the sum of the magnetic field and the magnetization inside the material is equal to the imposed field. The magnetic flux is continuous. Alternatively, if we put an object in a magnetic field which is oriented tangentially, then the field inside the material is much larger than the surrounding field, and is the sum of the surrounding field and the magnetization within the material. Okay, let's start out with the magnetization just in valence metals. I'm going to tell you about this for completeness. These things are not important much in engineering applications. If you have to worry about very subtle fields, they would be, but not in real engineering applications. And that's what we call diamagnetism and band paramagnetism. Diamagnetism. If I put a magnetic field onto a material, then that magnetic field via the Lorentz law will induce circulatory motion of the charges that are in the material. And that circulatory motion is in such a direction that it induces a magnetization in the material that opposes the field I put on it. When you put a field on a material, I spontaneously set up a field inside that opposes the field I placed on the material. This induced field is very small in most materials, so we don't worry about it. The one place that it gets to be big, and the reason it's small is that this Lorentz force is not all that big. It's trying to drive a current in a circle, and the current flow is resisted by the resistance of the material. So you don't get that much current, you don't cancel that much of the field. The diamagnetic effect is relatively small. The one exception to that, suppose this material has no resistance. If the material has no resistance, then this induced current is going to build up and build up and build up until it becomes so large that it cancels the entire field coming in. Well, a material that has no resistance is a superconductor, and this phenomenon is what's called the Meissner effect. If you have a superconducting material and you put it in a magnetic field, the magnetic field is excluded. Diamagnetism is perfect. And that is the phenomenon you've probably all seen, those experiments where you take an oxide superconductor and you put it on a ferromagnetic material on top of it and put it in liquid nitrogen, and the ferromagnet levitates. Well, that's the reason it levitates. The superconducting material will exclude the field. And the only way it can exclude the field of the ferromagnet is push the magnet up in the air. So you get levitation because of the diamagnetic effect. But in typical metals, this diamagnetic effect is very small. This gives you a susceptibility chi. I don't know if I told you, M is chi h, the magnetization of the material is chi times the imposed field. Diamagnetism gives you a very small magnetic susceptibility, except in superconductors. The second thing I'll just tell you about, because it's not that important really, is band paramagnetism. In normal situation, in the band structure of a material, of course, every state can have two electrons, spin up and spin down. And in the normal situation where the electrons find their lowest energy states, the lowest energy states are going to be occupied as much as possible. So I'm going to have a spin up and a spin down electron in every low energy state. But now let me put on a field. Turns out if I put on a field, the electrons that have their Bohr magnetons aligned with the field get a kick from the field and a lower energy. The net result is, in the absence of the field, here I plotted spin down, here spin up, and they're balanced. If I put on a magnetic field, and assume the magnetic field is up, then the electrons that have spin up will lower their energy. As a consequence of that, they will end up having more electrons spin up than spin down, and there will be a small magnetic effect. This is called band paramagnetism. It has a few consequences in engineering, but no real important applications. Where we get real magnetic properties is when we have core magnetism, uncompensated electrons in the core of transmission metals or rare earths. And we'll stop there and we'll pick up with this subject in Wednesday.